In this example of partial neutralization, we're just going to be looking at a bit more complex of a reaction because there's not a one-to-one ratio of hydrogen ions and hydroxide ions being supplied by the acid and the base. So in this example, we are asked to calculate the pH of a solution made by mixing 3.7 liters of 2.68 molar sulfuric acid and 3.4 liters of 1.9 molar aluminum hydroxide. So I just started off here by pre-writing the reaction equation and balancing it. So we know that neutralization is double displacement. We're going to form aluminum sulfate and water. Being able to predict that and balance it, that was covered in a previous unit, so I'm not going to go over it. A good first step for us in solving this, though, we will look for the ionization and dissociation equations for the acid and for the base, just to make sure we know what ratio of the ions are being produced. So sulfuric acid is going to ionize into 2H plus and 1 SO4 2 minus. And then the aluminum hydroxide will dissociate into that 1 aluminum 3 plus. Again, the charges are from the common ionic states of the elements. And 3 OH minus. So just keep that in mind. There's not a one-to-one ratio in this example. Here there's 3 hydroxides for the base, and there's 2 hydrogens from the acid. So that'll come into play later. So our first step should be to find the moles of sulfuric acid and the moles of aluminum hydroxide. So that's going to be concentration times volume, which is 2.68 molars or moles per liter times 3.7 liters, which is going to be, when you type that into your calculator, we'll get 9.916 moles. Again, I'm not going to round it yet because I want to make sure we carry as many decimal places as possible to get more accurate data later. And then for the concentration of aluminum hydroxide, that's going to be 1.9 molar, same as moles per liter, times 3.4 liters, which is going to give you 6.46 moles. Alright, so now what we have to keep in mind is that we'll look to the ionization and dissociation equations over here based on the number of moles that we've made. So we know that for the acid, there are 2 hydrogen ions produced for every 1 molecule of sulfuric acid, and there's 3 hydroxides produced for every 1 molecule of aluminum hydroxide. So what that means is that for sulfuric acid, so the moles of H plus is 2 times the moles of sulfuric acid, because there's a 1-to-2 ratio of sulfuric acid to H plus, and that's going to give us a value of 19.832 moles. And then for the moles of OH minus, same deal. There it's going to be 3 times 6.46 moles. And again, in there it's 3 because there's a 1-to-3 ratio of the base to the hydroxide anion. So that's going to give us 19.38 moles. And then again, we've seen this in the previous example, but the net ionic equation for a neutralization reaction is H plus OH minus gives you water. So in a neutralization reaction, there is a 1-to-1 ratio of H plus to OH minus. So once again, this kind of becomes a little bit of a limiting problem. So we can already look and see that there are more moles of H plus than OH minus. So there's going to be a surplus of hydrogen ions. So since there's a 1-to-1 ratio in the neutralization, that's why we can do, I'll just rewrite it this way so it's a bit more clear. That's why we can just subtract the moles of OH minus from the moles of H plus. So that's 19.832 moles minus 19.38 moles. Which gives you 0.452 moles. So there are 0.452 moles of H plus left over. So that's the moles. And then we want a total volume of the solution. Right, because we're asked for pH. So we're going to need a concentration, and concentration is moles per volume. So if we have 3.4 liters, I'm just looking at the question, 3.4 liters and 3.7 liters, that makes the total volume of the solution equal to 7.1 liters. So then the concentration, this is very similar to the one we looked at before, only we don't have to go from POH to pH. So the concentration of H plus, or C there, is N over V. So N over V equals 0.452 moles divided by 7.1 liters, which equals, when you type that into your calculator, you are going to get something equal to 0.0636662. I just rounded it off a little bit, so that'll be in moles per liter. I'm not rounding yet just because I want a bit more accurate of a value for pH. So that there is the concentration of H plus. Final step, pH equals negative log of the concentration of hydrogen ions. And we know that's what that is, the 0.063662. So negative log of that value when you type that into your calculator, you take the log of that. Right, and then again we have two negatives, so they're going to cancel out. You're going to get the pH being equal to 1.1961, or we'll round it off to 1.20. So therefore, the final pH of the solution is 1.20, which is very, very acidic. So since we've already seen an example of this, we can go back and just quickly review. We needed a balanced equation, ionization and dissociation equations for the acid and the base. We calculated the moles of the acid and the base, used that to determine the moles of H plus and OH minus, figured out what was in excess and how much of a surplus is there. That's the concentration left over that was not neutralized. Use the total volume of the whole solution to figure out the concentration, which we then put into the pH formula, and then it gave us a final pH. So the pH is quite acidic, and then you can also check conceptually that makes sense by thinking, okay, if I have the concentration of acid that we're given, even though aluminum hydroxide dissociates to give you more hydroxides, it does completely make sense. The sulfuric acid overpowers it because there's a greater concentration of acid than base. So conceptually, it also makes sense that the final solution would have an acidic pH. So there is our second example of partial neutralization. We should now be able to attempt some more practice questions.